we can see your presentations and we can hear you well. So you may begin.
All right. So I would also like to start by thanking the organizers for putting together this very nice meeting. It's really great to see you all. While most of this work was done at Karlsruhe Institute of Technology, I actually recently moved to Ruhr University Bochum, where I took up a new position. So just to mention that, my new affiliation. Today I want to talk about two materials and the evolution of nematic fluctuations. One of them is the 1144, calcium, potassium, iron, arsenic 4, of which we've already heard yesterday, and then the hole-doped and extremely hole-doped 1-2 systems. This work was not done alone. It actually started while I was still a postdoc with Paul Canfield. On the 1144 system, crystals were grown by William Meyer. Then the second part, the 1-2, was really driven by Paul Wiecki, who's working with me as a postdoc, and all the great people at KIT. We've had great theoretical support from Morten Christensen and Rafael Fernandez and Faye, and some first principles input from Rozier and Ladislav. It always is interesting and I think encouraging to remind ourselves that with the iron-based materials, we have a lot of free phase space in the material side as well. So once we can play with substitutions, we can actually do many things. And I don't need to remind this community of the typical phase diagram of the 1-2 compounds. We've just seen that with a stripe-type magnetic order with a nematic phase with a superconducting dome. That's what we always have in the back of our minds. But let's look at the 1144 materials and how they are special. And this is, really comes up in contrast to the hole-doped 1-2s. So when we have a 1-2, we start with an alkali ion on the A side, and to hole-dope it, we alloy with an alkaline earth, and to hole-dope it, we alloy with an alkali element. Oops, tongue twister. So there is a mix of these two elements on the A side. We have a doped 1-2 compound. On the other hand, and that was the discovery in 2016, some of these elements, they don't mix. When there's a size mismatch, they separate in layers. So we have alternating, say, calcium, potassium layers as one example. So this is not an alloy. This is really a 1144 compound. And that has consequences on the symmetry. So now we have two distinct arsenic sites, one's close to calcium and one's close to potassium. That can be seen, for example, in the arsenic NMR spectrum. It also is seen in the structure. So we have a very detailed structural refinement, the height of the one arsenic plane and the other ones, they are distinct from the iron site. So they're shifted out of their symmetric position here. So we lose the central symmetry. We of course still central symmetric, but we lose the I for MMM from this one, and we end up with a P4 of MMM. The 1144 pure is a beautiful superconductor, 35 Kelvin. So this is single crystal data from the Canfield group. But what we are wondering is, can we get magnetic order in 1144? And there have been some hints. They were from Rozier's calculations, actually, when she tried to reproduce pressure data taken and published here, that she did need magnetic fluctuations to get the correct structures. So if we want to know how to get magnetic order out of these magnetic fluctuations, we went back to this analogy. And I show you here a phase diagram of the hole-doped 1-2. And we are here on the right-hand side. Sorry. So we are here on the right-hand side. By charge count, we are equivalent to the 50-50. If we want to go towards magnetic order, now we need to reverse, we need to electron dope. And we can achieve that by substituting with, say, cobalt or nickel for the iron. So to do that, let me just plot this inverse and put the phase diagram. And what I will talk about today is the nickel substituted calcium, potassium, iron 4, arsenic 4. The phase diagram we found upon nickel substitution indeed shows some magnetic order. What we find is the suppression of superconductivity. One might think half a superconducting dome, maybe, and we find a magnetic phase coming up here. This magnetic phase was identified to be not the stripe type order as what comes to our mind when we think of iron-based materials, but no, it's what's called spin vortex crystal magnetic order. That was also mentioned yesterday. In the iron plane, the magnetic moments form this non-collinear pattern, and when you go around an iron plaquette, the orientation winds. So that's where this vortex vorticity comes from, and the name. And there is actually two types, and this one with some all-in, all-out structure was where we named it hedgehog type, some visual. This was also later confirmed by neutron diffraction. So now we have a variety of magnetic orders in the iron-based compounds, and to give an overview and some systematics, let's go to some theoretical description. To describe this order, and that was done long ago, we can use two spin density waves. One with two equivalent wave vectors and two different order parameters, M1 and M2. To recover the stripe phase, one of these order parameters is set 0, and then we get our stripes. But in the Ginzburg-Landau approach, there's different coupling parameters, and in the phase space of these coupling parameters, we find different magnetic orders as well. There is this spin vortex crystal magnetic order, where the two order parameters are perpendicular to each other. And that's where the non-collinearity comes from. There's another one where they are parallel and of equal size. That's a spin charge density wave, what it's called, or C4 by some experimentalists. But today we are going to talk about this area here. And where does the 1144 structure come in here? If we look at this, the two distinct arsenic sites and the iron plane, I put again the magnetic structure, and now I add the arsenic atoms. They are symmetry inequivalent, they're distinct. So now this provides some sort of field. That field must be aligned along the z-axis and also has some staggered symmetry. So every other iron plaquette, there's a different arsenic site. So it really turns out that this causes a symmetry breaking field that couples bilinearly to the spin vorticity, the cross product of these two magnetic order parameters. And in consequence, I have to change my free energy expansion here. I add another term with this field eta from the symmetry, different symmetry in the 1144 structure. So in the 1144 structure with a finite eta, this spin vortex crystal phase is enlarged because of the coupling. And that's where this relation comes from. And we're wondering what's the effect on the nematic fluctuations of this spin vortex crystal structure and of this additional eta field. There have been some calculations by Morton and Fay, and let me quickly walk you through that. For all the caveats and approximations, I refer you to the archive. So what's plotted here is the calculated nematic susceptibility on a path through that phase diagram as function of a proxy temperature down to a transition. Here, the transition in 0 eta field. So we see deep in the spin vortex crystal phase, there is a finite nematic susceptibility. It's increasing and then it's cut off at the transition. It doesn't diverge. And once we add a field eta, it gets suppressed and the transition is washed out. If we are deep in the stripe phase, the eta field has basically no effect or has no effect at all. In this intermediate one, it suppresses the transition. We go from a divergent nematic susceptibility to a non-divergent one. And the ground state changes from stripe to spin vortex crystal. But what we were wondering is what will this look like experimentally? So here's our phase diagram again, and I want to emphasize this is a phase diagram, or this is a large phase diagram. We go from a TC of 35 to fully suppress the magnetic order. There is no orthorhombicity, there is no nematic order, there is no stripe type magnetic order. So here we are fully tetragonal, and we were still wondering what's the nematic susceptibility in this fully tetragonal phase diagram. And we are looking at elastic resistance and elastic modulus measurements. Elastic resistance I don't need to introduce anymore, thanks to the previous two talks. And we opted to measure two different crystals that are mounted perpendicularly to each other on a piezo stack and a pair of crystals for each crystallographic direction. So here I showed sort of the longitudinal and transverse elastoresistance for one specific composition as an example. From this data, you see, well, the coefficients are fairly small. There's a sign change between longitudinal and transverse, another one between the two crystallographic directions. And to obtain the symmetry components of the elastoresistance tensor, the sum, the A1G component, that's basically the sum of the two. And we see, because of the sign change, that will largely cancel out. While the B1G and B2 components, that's the difference of the two, that's the ones we are going to look at. And again, that was just mentioned in the previous talk, or it was important part of the previous talk, the B2G elastoresistance coefficient is proportional to the B2G nematic susceptibility. That's the one that's related to our stripe order. So when I do this, here for the one example, the B2G and the B1G elastoresistance coefficients related to this different strains, and that's the doping evolution all over the phase diagram. First of all, the B1G doesn't evolve at all. So it does not depend on the composition. It's unaffected by whatever drives this phase diagram. So there's no interactions there that we will not look at this one. On the other hand, the B2G, that's quite interesting. There is a very pronounced evolution of behavior here, different temperature dependencies, different signs. So let's take a look at that. And I will do that first of all by plotting it in a color plot here over the phase diagram. Notice I flipped the phase diagram. So here's the magnetic phase. We see a sign change, but the nematic susceptibility does not change sign. This has to be the proportionality constant. If we compare that to the cobalt barium 122, there's no sign change here, but there's a significant change of magnitude of this elastoresistance coefficient. And the influence of this prefactor was just recently discussed, well, just 10 minutes ago in the talk and these recent papers. So here we have a case, there's not only a magnitude change, there's a real sign change of the proportionality constant. And that's reminiscent of a result in the whole doped 1-2 system. Here there's no elastoresistance data published to date, but there is a resistance anisotropy in strained or stressed samples. And the sign change was found there as well. So that seems to be related. And that comes from microscopic measurements of well, scattering and Fermi surface changes, which was also explained here. So what we also see is that in vicinity to sign change, the temperature dependence becomes rich. So there's a sign change as a function of temperature as well. And that must also be related to this prefactor. But we think that maybe if we go far enough away from that sign change, we can learn something from the temperature dependence of the elastoresistance, which, well, we can learn something about the temperature dependence of the nematic susceptibility from the temperature dependence of the elastoresistance on these extremes compositions. And that's what I've shown here. And as is customary in the field, I tried a Qrevise fit. For the optimum TC sample, the undoped 1144, well, Qrevise is approximately working, but there's strong deviations, especially at low temperature. For the nickel dope one, which would correspond to an underdoped 1-2, there's a beautiful Qrevise law that works very well. So again, this is reminiscent and familiar from what we know of the 1-2 compounds. This optimally whole doped barium 1-2, it looks very similar to this optimum to C1144, even the way this deviates. While the underdoped 1-2 they show a very nice Qrevise law down to their transition, same as here. So this is a very, very familiar behavior. But while we still don't really know about this prefactor, we thought we might try a different probe, the bending modulus, where this resistance prefactor does not enter. what we have here is the same equation that Matthias just used. The nematic susceptibility influences the elastic shear modulus. And with this coupling constant, this combination is dimensionless, and it has to be 1 at the transition. At the nematic transition, the shear modulus vanishes. So we have some handle on the units here. What we actually measure is not the shear modulus, but the Young's modulus, which also has some other non-critical elastic constants, and we try to get a handle on that using the first principles calculations input. So let's go to the results. This is the optimum TC samples, the pure 1144. You see a softening of the Young's modulus, which comes from a softening of the shear modulus and a significant hardening below TC. And this is very similar to the 1 to 2 that corresponds at similar doping level. Very similar temperature dependence. On the other hand, the nickel doped, or what would be an underdoped one with a magnetic transition, I do know what will be the temperature dependence of the Young's modulus if there's a Qrevise-like temperature dependence of the nematic susceptibility, and that's what this red curve shows you, and it works very well. So here again, we have evidence for a Qrevise-like divergence of the nematic susceptibility. There is a very curious, very subtle anomaly at the spin vortex crystal magnetic phase transition here. So what does it mean for the nematic susceptibility? This is estimates for the nematic susceptibility from these data. There's a few parameters here, but the qualitative dependence, temperature dependence doesn't depend significantly on these parameters. So we are very confident about how this looks like. The nematic susceptibility in this one compound, this pure one, increases but saturates, flattens, and then decreases below TC. That looks like a sign of competition, as we are very familiar with already. The nematic susceptibility in our doped 1144 increases in a Qrevise-like manner, but is far from critical. Remember, this has to be 1 at the transition, so we are much below that. Then at the transition, there's this subtle anomaly that almost looks like an inflection point, or it does look, there is an inflection point here. And it's tempting to compare that with our model calculation, where in the case of finite eta field, which we have in these compounds, there is also predicted to be an inflection point of the nematic susceptibility at the transition here. So to make the connection becomes tempting. So let me summarize my first part. Phase diagram of the 1144 and the B2G elastoresistance coefficient here. On the high nickel content side, the magnetic system, we do find finite nematic fluctuations, even though this is all tetragonal and the transition is also to a tetragonal magnetic state. And these fluctuations are far from critical. But they nevertheless have a Qrevise-like temperature dependence. On the other hand, we find evidence for a, let's call it sub-Qrevise-like temperature dependence of the nematic fluctuations. On the optimum TC sample, it's very similar to the hold of 1 to 2, the equivalent one. And we think that might be a result of close to the general magnetic orders being close to the transition line between the SVC phase and the stripe type phase. Overall, most striking is here that we have an example where the prefactor of the elastoresistance changes sign in a composition temperature in a phase diagram, and also becomes likely temperature dependent, at least in a part of this phase diagram. So to come to the second part of my talk, which will be a bit shorter, is, well, we want to go to the other direction. What happens if we go more hole-doped? And something is known about this. Frederick Hardy from Karlsruhe published this in very much detail. Here is again the barium potassium 1 to 2. We can hold up to the extreme. We end up with pure potassium iron arsenide. We can go with further, now vertically in the periodic table, so apply chemical pressure to the rubidium and the cesium compound. And if we go in this direction, we see that the Sommerfeld coefficient, the specific heat coefficient, the effective mass or measure of the correlations goes up quite a bit. So these are very large values. This comes in the region of heavy fermion compounds. The resistance also looks similar to heavy fermion systems. There's a huge triple R, and there's a almost, well, quadratic or power law-like temperature dependence at low temperature here. And there are superconductors around 2 or 3 Kelvin. There has been a recent report about nematicity in these compounds, going from the barium directly to the rubidium one. And what was reported is a flip, a change from a B2G type nematic behavior to a B1G type nematic behavior. So a flip of the nematic directions, measured using, well, deduced from elastic resistance measurements. We wanted to start with the most extreme compound, the cesium-122 here. And there is another interesting property of this. It has not only a huge Sommerfeld coefficient, it also has a huge Grüneisen ratio of the Sommerfeld coefficient. We just talked about Grüneisen ratios, which is here the in-plane pressure derivative of the Sommerfeld coefficient. And as a consequence, or almost analogous to this, the thermal expansivity, the alpha coefficient here, is huge in the cesium compound. And I can plot not the alpha, the thermal expansion coefficient over temperature here. I can also plot simply the length change. What we see in the cesium-122, it shrinks a lot on cooling. It shrinks almost twice as much, or more than twice as much as a copper metal, 4 times as much as barium-122, and very different from a piezo stack. So a sample on a piezo stack would already experience huge amount of isotropic strain. Not a huge amount. So we thought it might not be the best idea. And instead, we use a raisable strain cell that was also just introduced to compensate for this strain mismatch. By moving the 2 sample mounts closer together on cooling, which would be these red stars here, we can keep a sample in a strain-free state within the system. We see that the resistance follows the one of a freestanding sample. If we don't do that, we break the sample or change the state dramatically. So once we have a sample, say at low temperature in this state, we can then apply small strain sweeps and measure the elastic resistance. That's what we did again. And here we use an 8 contact configuration to get longitudinal and transverse resistance at the same time, inspired by this work here. And again, the same symmetry decomposition for the coefficients. And here's already a result for the cesium sample. So the longitudinal and transverse elastic resistance for a sample in 100 direction and in 110 direction. And you see differences to our previous systems. There's no more sign changes here. This means that the A1G elastic resistance is dominant. It's huge here in blue. And the B1G and B2G components are rather small, much, much less than the A1G. And what's really well, that was our first result. And secondly, we went to the evolution of this. We go again over this phase diagram from some optimally doped to the pure potassium, rubidium, cesium. In this one, which is still close to some stripe type, to the stripe type order, we see an increase of the B2G elastic resistance, very similar to what we just had. We have small A1G and B1G components. We go further, the A1G component starts to grow, the B1G shrinks, and the B1G shrinks, and there's a finite B2G shrinks, and there's a finite B1G. We go further, and we see this growth of the A1G component, the symmetric one, the in-plane symmetric one. The B2G one, that would be our nematic susceptibility, well, doesn't change very much anymore. It's there. And the B1G is finite as well, but does not diverge. There's no Qrevise or power law dependence here. So the A1G component, that compares very well to our Grüneisen ratios, or even in temperature dependence, the thermal expansivity here. And there's a fundamental reason for that. It is that the resistance in these compounds is strongly dominated by the entropy. And so with the elastic resistance, the A1G coefficient, we actually get a measure of the Grüneisen ratio here. So this brings me to the summary of my second part. In this evolution, we see a growth of the A1G elastic resistance systematically towards the cesium-122, which is related to the enhanced Grüneisen parameter, while the B2G simply diminishes and the B1G component is finite but never diverges. Thank you very much.
Thank you, Anna, for this beautiful talk. Any questions from the audience?
Yes, can I ask a question?
Yes, go ahead.
Okay, Anna, thanks for the very nice talk. I have a question with respect to the first part. So when you talk about the doping, maybe you mentioned that, but I just missed. So in principle, when you dope with nickel, I guess that you're also introducing some extra magnetic moment. Does something is known about it? That whether the nickel is magnetic when you dope it in the 1144, and in that regard, when you did when you refer to theoretical modeling, I guess that did not take into account the fact that nickel is actually introducing another magnetic impurities into that.
Okay, I think there's two components. No, the theoretical modeling did not take that into account. When you talk about magnetic moments, I think the role of nickel in this 114 is just the same as nickel in the 122s, and that was studied quite in detail. It is an impurity. We see an enhanced residual resistance. We see enhanced scattering. It does not...
Yeah, there's no moment on
look like exactly. There's no magnetic moments there. It's an impurity. It's an impurity in the iron plane, so it's quite significant, but it's there's no magnetic moments extra.
I see. Okay, thank you.
Qimiao is next.
Yeah, and a beautiful talk. So in anticipation of some discussions we'll likely have in the next session about the last part that you talked about, I just want to understand make sure that I understand what you said. So the A1G contribution looks like there's a strong temperature dependence, but your interpretation is that it's in a way a background contribution. Is that a fair
well, it depends on what you call background. It's the A1G contribution that dominates. So when I measure longitudinal elastic resistance, when I measure just one sample, I will see a strong temperature dependent, but it comes from the A1G component.
Yeah, so the A1G component is the increase as the temperature is lowered, is not signifying any nematic tendency towards nematic order.
Correct. Because
it's just that because the overall state, for instance, if you look at the resistivity, there's a crossover happening around 50 Kelvin. And if you look at anything else, specificity is developing. Is that fair understanding of?
Yes. So this temperature dependence with this in the cesium with this peak or this large enhancement, this we see in basically everything. It's related to this coherence incoherence crossover behavior.
Yeah, it's something that I would see in heavy fermions, for instance.
Exactly, but it's a symmetric effect. It has nothing to do with distortions. It has nothing to do with nematicity.
And from experimental perspective, what's the subtlety in the assignment of the measured quantity to the components of these various components?
Well, there's different experimental challenges. The challenge here is that one component is small, so to get it out accurately, that's not so easy. What you do in practice is you measure two directions and take a difference. And then it depends on misalignments, maybe. That's one challenge. We use a single sample for the two directions. That helps a bit. It doesn't affect the conclusion that the A1G component is dominant. It makes it difficult to get the exact temperature depends on the exact size of the subdominant contributions.
I'm just maybe I can sort of some theorists. I don't have a way of thinking about the configurations, but I can count. So is there is there a difference in terms of how many independent quantities that when measured that would allows one to either accurately or less accurately extracting doing this decomposition? In other words, does everybody measure the same number of independent physical quantities, or the different groups measuring different number of independent
Well, I think you always need to measure two directions to do this. There's different ways to do that, and maybe John Hall can support me here. But in principle, it's always two quantities and the difference of two directions, no?
Yeah, I think the NS measurements for applying strain along two different directions and still seeing a gigantic response is quite convincing. Showing that it's a A1G channel. Yeah.
Okay.
I mean, in principle, there's there's other method as well.
Yeah,
I can further corroborate this, but I think so far the data is quite convincing.
Thank you.
Yeah, I think Ming is next, and then Pavel, and then Amalia.
Really good, nice talk. I just have a question about the first part, 1144. I'm just curious, how high in doping can you dope the nickel? Can you say, for example, go all the way to the end, a complete substitution?
No, unfortunately, no. This becomes already hard beyond the 5% nickel. So the 7.5, the crystals already become smaller, and we have not managed any further. We chose the nickel because, well, we get more electrons per 5%.
I see. So for the same story for cobalt, I guess?
Yeah, for cobalt you can dope more, and then you finish around 12%. So
I see.
unfortunately, we have not managed to go any further.
I see. The other question is in the other type of the underdoped potassium doped barium 122, even in the C4 phase, there's been PDF measurements that shows that locally the crystal is still orthorhombic.
Correct.
Do you know for this material 144, the same story? Or
I don't know about PDF measurements, for example, in this. It's possible that I missed that. Well, since the nematic susceptibility seems to be finite, I don't see why it should not be locally distorted. Yes, then it's a matter of degree.
okay.
All right, Pavel is next.
The divergence of the Grüneisen ratio is often associated with some quantum criticality. So in the cesium compound, is there anything like that going on anywhere nearby?
That's a really good question, and something which we have been puzzling about together with Xim Yao, for example. So yes, this looks like as a function of chemical pressure. We could go towards such a point. The problem is in terms of physical pressure, that's tensile. So it's not something we can experimentally do very well. We don't know if there was an ordered phase nearby and which one that would be, but it's a question we are looking into, and it's an open question, I would say.
So like any magnetism or it's not known so
We haven't
far.
known. We haven't found it. No.
Okay, thank you.
Okay, finally, Amalia.
Thank you, Anna, and congratulations on your new position, first of all. So my question is more technical. So you're using both the piezo stacks and the razor bill cell. So when you use the razor bill cell, that applies extremely large strain, which takes you outside the linear regime and where you can define a nematic susceptibility. So I just wonder, how much strain is applied with the razor bill and what limit you are working in that regime.
Okay, so in all of this talk we stayed in the linear regime. In the razor bill, we need this huge strain range to compensate for the huge thermal expansion. So in the end, there's not much left, at least on the tensile side. In one of the directions, there's not much left because we need it all to compensate for its thermal expansion. So far in the cesium, it doesn't look very nonlinear until it breaks. Which isn't, yeah, okay. Can happen earlier sometimes.
Thank you.
Let me just comment that we also do a lot of measurements on the cobalt barium 122, and then it's really strange that it still show a very linear behavior up to a very large anisotropic strain. Any more questions? Okay, if not, then let's thank Anna again.
Thank you.
And yeah, I think we also conclude our morning sessions for today. And we'll see you 8.5 hours from now for the final sessions of the Ironbased symposium.
Thank you.
All right, congratulations on your new president, guys.
It's official.
It's officially happened. Well,
While Anna was speaking, so thank you.
Thank you,
Thank
guys.
you for being here and not.
we're very
Yeah,
happy.
you were competing with Anna. You were competing with Joe Biden.
Yeah, right.
Good. Great to see everybody. Hi, Ian. Good.
Okay. So I'm not sure I can make the midnight, 3 in the morning discussion round.